Okay, good morning. This is our 30th session, and today we will start a new topic which is called as dimensional analysis. Okay, so any one of you have heard this name before? What do we mean by dimensional analysis? Okay. Okay, so basically what happens, as you have already seen, we are having the Navier-Stokes equations which actually governs the fluid flow for different kinds of problems. Okay, and then we have also seen from the previous discussion that for some of the physical scenarios, what we do basically, we try to simplify the Navier-Stokes equations and then we try to find their theoretical solution. Okay, and once we have theoretical solution, then we can simply substitute the parameters which are affecting our flow field variables, which are variables of our interest, and we can determine their behavior. For example, if you have to study that how much will be the maximum velocity or average velocity in a pipe, then if you simply know a parameter pressure gradient, then corresponding to that you can get the value of the velocity profile. Okay, but what happens, the solution of, or in other words I should say, the analytical solution of these Navier-Stokes equations is applicable for very simplified uh, kind of physical scenarios. Okay, whereas in majority of the physical situations, either the assumptions which we made, these may not be fully true, or the situation will be so complex that we will not be able to simplify or remove the terms in Navier-Stokes equations which are bothering us and not allowing to calculate their solution theoretically. Okay, so that's why we have to go for the other approaches which I have already told you in our initial lectures. The other two approaches are nothing but experiments and numerical simulations. Okay, and of course when you do experiments or numerical simulations, then there are actually cost involved. Okay, so if you do experiment, you have to develop experimental facility, you have to spend time with it. Okay, and you have to also spend some amount of consumables which will be consumed in each experimental run. So you have to also bear some cost of that. And if you do the numerical simulations, then of course you have to use the computational resources, and computational resources also comes at some cost. Okay, so if you are using your high performance computing system, so of course that will be involving some amount of cost. Okay, so that's why it becomes very important to somehow relate a group of variables in the form of dimensionless quantities. So this serves multiple purpose. Okay, for example, if I consider that, say I have F, and F is nothing but force acting on a submerged body in fluid. So I can consider that, say I have a cylindrical body, and over this cylindrical body, if I have flow of fluid over here. Okay, so in this scenario what will be happening? Of course this fluid will be subjecting some amount of force on this body. So if I have to determine this force, let's consider that this force is function of density of the fluid, it is function of viscosity of the fluid, it is function of, say this dimension is length scale of this object, so it is function of length scale of the object. Okay, and of course if I consider that v is my velocity of the flow stream, then of course it will be function of velocity of this flow stream also. Okay, is this point clear? So in this scenario, you can say that our variable of interest is force, and to study this force on a body which is submerged into the fluid, this force is affected by number of variables, and two variables over here are related to the properties of the fluid, which are nothing but density and viscosity. Another variable is related to the length scale of the body which we have considered, and say another variable is actually velocity of the flow field. Okay, so what you have to do, if you have to say do a experiment or a numerical simulation to study the effect of all these variables on the force which is acting on this body. So what you can do, you can first, in this situation, you can first only vary the density. Okay, first what I have to do, I can keep my mu L V all parameters constant, and I will be simply varying the density. And upon varying the density, what I can do, I can plot force along ordinate and density along abscissa, and then I can try to plot a trend that for different values of density of the fluid, how my force is actually varying. Okay, so it may be like this, say my this is one experimental point, this is second experimental point, third, fourth, fifth, so something like this. And if I draw the trend of these experimental points, that will be giving me the relationship of between the force and the density. Is this point clear? So now in this scenario, when I was calculating this effect of density, I had actually kept my mu L and V as constants, because then only I can say that this is solely the effect of density when other parameters are kept constant. Okay, so when we do this type of dependence, so if I have to plot this trend, so this trend will be giving me a good curve or good fitting of the data points only if at least I require about 10 data points over here. Okay, so say that is my minimum requirement of about 10 data points, then only I can get a smooth trend so that I can fit these experimental points with a good line, okay, which is almost mimicking the experimental behavior. Fine. So this way you have come to know that I have to vary how many densities? 10 densities. So it means that I must have 10 fluids which are having different densities but same viscosity, because viscosity we are trying to keep constant. Okay, then second effect, what I can do, I can now vary viscosity and keep all other parameters constant. So then it will be 10 viscosities and then other parameters are constant. Then similar way I have to consider the 10 different sizes of this particular cylinder. Okay, then I have to consider 10 different velocities. So that way if you have to do the experiments, how many number of experiments do you expect over here? No, you need not to do only for a single case. You need to vary these 10 different densities for all the 10 set of viscosities, for all the 10 set of lengths. So it means this way you will be having 10 to power 4 numbers of experiments. Okay. Now here comes the advantage of dimensional analysis. If I apply dimensional analysis over here, so whatever the equation I have got over this particular equation can be simply reduced to this form: F divided by rho V square L square is some other function G. So earlier the function was F, now it will be some other function G of rho V L by mu. Okay. So now if you see the dimensions of this, so if we have to represent the dimension, we are having actually 4 different fundamental quantities. Okay. First fundamental quantity is mass, which can be represented with m. Second is length, which can be represented with L. Third is time, can be represented with T, and fourth is temperature, which can be represented with theta. Okay, so if you try to represent now these dimensions in terms of these 4 fundamental quantities, what you will be finding? So force is nothing but mass into acceleration. Okay, so mass can be represented with m, fundamental dimension. Acceleration, meter per second square, so length L into T minus 2. Okay, so that is the dimension of f. Now what will be dimension of this whole quantity? Dimension of rho will be ml minus 3, v square, velocity square will be L2 T minus 2, L square will be M2. Okay, so now what it formed? What it forms? Is it correct? Okay, density will be kg per meter cube. So kg means m and meter cube means dimension of L cube, and then I have square of velocity. What is velocity? Meter per second, Lt minus 1. So it will be L square T minus 2, and then I have, this is I am writing wrong, L square, it will be as it is L square. Okay, is this point clear? So now if you see, the dimensions of numerator and dimensions of denominator both are same. So it means this quantity f by rho v square L square is nothing but a dimensionless quantity. This is not having any, so it's a dimensionless quantity. Okay, and similarly if you do for this rho vl, what will be rho vl? Rho is ml minus 3, v is l t minus 1 into l. What about mu? What is the unit of mu? Pascal second. Okay, that is the unit. So what is Pascal? Force per unit area. What is force? Mass into acceleration. So mass, acceleration will be Lt minus 2 per unit area. L minus 2 into T. So that is fundamental dimension of viscosity. Okay. So now if you see, this should also cancel. Is it cancelling? M is cancelling. Here I have T minus 2 and T. Yes, T is also cancelling. L is becoming minus 1. Correct. All are cancelling out. So it means that my this group rho VL by mu is also a dimensionless quantity. This is also a dimensionless quantity. Okay. So this particular first term, which is F divided by rho V square L square, is called as coefficient of force, and this term, which is G of rho VL by mu, this is nothing but my another dimensionless quantity, which is called as Reynolds number. Okay. So till now, what I have done, whatever the number of variables I was having, these, how many variables were there? 1, 2, 3, 4 and 5. So I was having 5 variables. Okay. And one was my output variable. So input variables I considered 4. That's why I was supposed to do 10 to power 4 number of experiments. Now I have seen that all my variables have clubbed together into nothing but 2 dimensionless parameters. Okay. So 2 parameters I am having. One is this, another one is this. Now I need not to study the behavior of individual parameter like density, velocity or length. I can simply study the effect of as a whole of this quantity, which we are calling as Reynolds number, and I simply need to do only 10 experiments to get a smooth trend in between dimensionless force coefficient and the Reynolds number. So 10 to power 4 number of experiments have now reduced to 10 experiments. Okay. So the idea is, in generic sense, if I can say that if I have n variables, then ultimately my idea is to get k dimensionless parameters, so I will be having how much? N minus k number of reductions. So that is the overall idea. So now in the previous discussion what I have done, initially I have shown you 5 variables, then I have shown you 2 dimensionless groups. But what is the process of doing that? That is something which I have not yet explained. Okay. So the idea is, the whole idea of dimensional analysis is that in any physical scenario, if we are considering all the variables which are affecting that physical scenario, okay, so the process of reducing the number of variables by using some compacting techniques, that is something which we call as dimensional analysis. Okay, is this point clear? So that is something which we call as dimensional analysis. Now it is having many benefits. So the very first benefit which we have seen over here, without knowing the process, I have just given you the final forms. First is the more number of variables, and then second is the k group of dimensionless parameters. Okay, so by knowing this simple example over here, we can clearly see that the first benefit of dimensional analysis is that it has actually reduced the requirement of number of experiments. Okay, second important, so if number of experiments or number of simulations requirement is actually reducing, so it means our cost involved, time involved has reduced. Okay, second important advantage of this is that you will be finding that in your may not be at the moment, but whenever you will be studying the more complex situations where heat transfer is also involved, for example, if you go for this convective heat transfer where fluid flow and heat transfer both are coming together into the picture, then you will be finding that your number of parameters may go to very large. Say you may have about 10 or 12 parameters. Okay, so if you are having 10 or 12 parameters together, it will be very difficult for you to understand the phenomenon or theory with the help of interpretation of these. Okay, so one better way is, if we can club together the group of parameters in the form of dimensionless groups, then first I can only study the behavior of individual dimensionless groups on our output parameters. So that way I will be able to make some theoretical interpretation of my experiments or simulation results. Okay, so it will be also helping us in designing how we can perform experiments and simulations. And of course, within the single dimensionless parameters, we can see that how different terms are actually relatively coming into picture. Okay, then third important benefit of this is that it allows us to go for scaling approach. What is the meaning of scaling approach? Say my aeroplane is flying in the air. Okay, so of course on the aeroplane some forces are acting because of the fluid flow. So what I will be doing, if I have to determine what are the forces which are acting on this aeroplane, if I have to do the experiment, then do I need to prepare the complete prototype of the aeroplane and then perform experiments? If I don't use the principles of dimensional analysis, then of course I have to do. Okay. But if I use the principles of dimensional analysis, then actually in place of creating the complete physical prototype of a system, I can develop a small model, and then whatever the outcomes I have got for that particular model, if I keep my input parameters the same, then I can simply convert these outcomes from model to a prototype. Okay, so if I explain you this previous case, so say F by rho v square L square was nothing but the force which is acting on the submerged body, and we have come to know that it is nothing but simply function of Reynolds number. Okay, so now if I consider two similar scenarios, that one side I have a model and other side I have a prototype, actual prototype of a system. Okay, say aeroplane. So if I have kept the flow Reynolds number of the model REM and REP is flow Reynolds number of the prototype. Okay. Now if I consider that Reynolds number of the model is equal to Reynolds number of the prototype, because this is nothing but a dimensionless quantity, so then I can clearly say that this function of Reynolds number for model will be equal to function of Reynolds number for prototype, because these two are dimensionless quantities. Okay, so this way what I can do, if this function is equal, then I can simply write that force on model divided by density for model, velocity square for model and length square for model can be equal to force for the prototype divided by density which we are using for prototype and velocity as well as length. Okay, so ultimately I can say that the force which will be acting on the prototype, that will be nothing but equal to force acting on the model times density of fluid which we are using for prototype divided by density which we have used for model times Vp by Vm square and Lp by Lm square. So this is the third important advantage of dimensional analysis. It creates similarity between the model and the prototype. Okay. So whatever the outcome will be there for a small scale model, same can be extended by keeping the same values of dimensionless parameters and then using the corresponding transformations of the scaling variables, and that way we can actually predict the values for the prototype. Okay. Now after knowing the advantage of dimensional analysis, we have to also see the procedure of dimensional analysis, but before that we must know that what kind of equations are there on which actually we can apply the dimensional analysis. Okay, so before applying the dimensional analysis we have to ensure that our equations must follow principle of dimensional homogeneity. Can you tell me what is principle of dimensional homogeneity? You have studied it before also. What do we mean by principle of dimensional homogeneity? Please tell me. The meaning is, if I have some equation, okay, which is having different terms involving the addition, then each and every term, okay, should have same dimensions. Simple example is our Bernoulli equation. If you see, so we are having P by rho g plus V square by 2g plus z equal to constant. Okay, now what is the dimension of this? L, 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 so of course C must be L. Okay, another simple equation, say displacement of a freely falling object, I can write it as S naught times S naught plus V naught times T plus half of G T square. Here what is dimension? L, L and L. So that is something which we call as principle of dimensional homogeneity. Of course, there are some equations which do not follow the principle of dimensional homogeneity. Not all, but there are very few equations which particularly are data driven. Okay, say if you do experiments and then after doing experiments, if you don't apply any physical theory and if you simply use the mathematical tool, say apply multivariate regression analysis or some other thing, then ultimately what you get? You get equation something like this, say A is equal to B power C D power E. So some equation, some combination you may get plus something else. Okay, so in this type of equations which particularly are data driven, which are empirically driven from the data, there you may find these peculiar type of equations can exist where principle of dimensional homogeneity is not satisfied. Okay, but whenever we are talking about the theoretical perspective, then you will be finding that almost all the equations will be actually satisfying the principle of dimensional homogeneity. Okay, now the dimensional analysis also I can apply only for the equations which follows the principle of dimensional homogeneity, because ultimately while we will be going through the procedure, then you will be coming to know that we are using the fundamental dimensions only in order to reduce the number of variables. Okay, so that's why this is very important principle, and our equations or variables should follow this principle, then only we will be able to apply it. Okay, then comes the next. We have two types of uh, things in our equations which are called as variables and constants. Okay, so some quantities are variable, some quantities are constant. For example, if I talk about this equation, then S naught, V naught and G, these are constants, whereas this S and T are nothing but variables. Okay, but variables and constants can also be of two types. First is, we may have dimensional variables. What is the meaning of dimensional variables? The variables whose fundamental dimensions exist. For example, if I talk about S, so S is not a dimensionless quantity. Its fundamental dimension is L. If I talk about T, it is a variable whose fundamental dimension is T. So which are not dimensionless quantities. Dimensionless quantities are those for which the fundamental dimensions M, L, T, theta have values 0, 0, 0. These does not exist. So these are called as dimensionless quantities. Okay. So all the variables which are having the existence of fundamental dimensions, these we call as dimensional variables. Then similarly, we may have dimensional constants. What are dimensional constants? Can you tell me from the previous equations what are dimensional constants? If you see S naught, V naught, what is S naught representing? Initial displacement. V naught is representing initial velocity. G is representing acceleration due to gravity. So all are nothing but the constant quantities. Okay, but all these constant quantities are having some dimensions. That's why these are nothing but dimensional constants. S naught, V naught, G. And if you are talking about the Bernoulli equation, then in Bernoulli equation this rho, because we are talking about incompressible fluid, so that's why rho will also be dimensional constant. If you talk about the same equation, then C is also a dimensional constant, because it will be remaining constant, the sum of pressure head plus velocity head plus potential head. So that's why C is also a dimensional constant, because its dimension is equal to L. Okay, then I can have some constants which we call as nothing but dimensionless constants. Okay, so typically dimensionless constants are those which do not have any dimension. So if you see the previous equations, yes, Reynolds number is a dimensionless constant, and in this equation also you can see this 1 by 2 term is there. So this is nothing but a dimensionless constant. This power t power 2 is there. So all the numbers are nothing but dimensionless constants. Other than that, as Reynolds number you pointed out, that is also means Reynolds number is not a dimensionless constant. That's a dimensionless variable, because you can vary it. Okay. Is this point clear? So all the numbers or other quantities which are having fixed values, these are nothing but our, say 1 by 2 over here in the previous equations. These are our dimensionless constants. Okay. Now, when we have to do this reduction, so if you see earlier I have given you directly the final formulation, but if we have to do reduction, so what we have to do basically, initially I will be considering n will be total number of variables and k will be, I have told you, the dimensionless parameters or variables, and n minus k will be my number of reductions. Okay. So first let's try to see this process through this basic equation which I have written. S is equal to S naught plus V naught T plus half G T square. First of all, write its fundamental dimensions. So this will be L, this will be L, V naught will be LT minus 1, and this T will be simply T. Here G will be LT minus 2, and it will be T square. So MLT theta are nothing but 4 fundamental dimensions. But if I consider in this equation, how many fundamental dimensions are actually coming into picture? So if I say only 2, L and T, all my variables are represented by nothing but only 2 fundamental dimensions. Okay. So I can say that in this system I have only 2 fundamental dimensions. So typically the number of fundamental dimensions are represented by symbol J. So I can say that my J is equal to 2 over here. Okay. So if J is equal to 2 over here, it means that I need to consider either 2 or less than 2 numbers of scaling parameters to non-dimensionalize the equations. Okay. What I am trying to say over here, if in all my variables, whatever the number of fundamental dimensions are involved, okay, so actually what I need to do, I need to consider either equal to number of fundamental dimensions or less than number of fundamental dimensions scaling parameters. The meaning of scaling parameters are those quantities which will be, when combining with the other variables, then forming the dimensionless groups. Okay. What is the meaning of scaling parameters? Scaling parameters are quantities, or I should say variables, which combine with one additional variable to form dimensionless groups. Okay. That we call as nothing but scaling parameters. And scaling parameters many times are also referred to as repeating variables. Why repeating variables? That will be clear in a moment. Okay. So these are also called as repeating variables. Say this is my equation. S is equal to S naught plus V naught T plus half GT square. I want to non-dimensionalize this equation. Okay. So as I have seen that in this equation I am having number of dimensions as 2. So I will first start with 2 set of parameters which can actually non-dimensionalize this. Okay. So of course, what is our interest in this equation? Our interest in this equation is to calculate the displacement of the particle as the function of time. Okay, so that is our interest. So I can say that S and T are nothing but my kind of output parameters which I am trying to study. But these parameters are affected by S naught, V naught and G. So if I have different values of S naught, V naught and G, then of course the values of S and T will be changing. So one common rule is that when we are trying to determine the scaling parameters, we should not take the parameters of interest. Okay, whatever the parameters which are acting as our parameters of interest or output parameters, we should not include these in my set of repeating variables or scaling parameters. So it means that S and T, these cannot go to repeating variables because these are my output parameters, these are my parameters of interest. Okay, so it means that I have now three choices. Either I can select S0, V0 and G. And how many I have to select? Only two, because my number of fundamental dimensions are 2. So my option 1 is I can select S0 and V0. Okay. So now S0 and V0 I have selected. I have to every time combine S0 and V0 with each variable so that I can form a dimensionless group. Okay, so if I consider my first dimensionless first variable is S. If I have to make S dimensionless, S is having dimensions of L, so I can simply write S by S0. If I use S by S0, then ultimately I am getting nothing but a dimensionless parameter. Okay, so S by S0 I will be calling as some dimensionless parameter S star. Is this point clear? Then I can go to this S0. Okay, S0, let's not go now. Or even if I go to S0, then ultimately what I will be getting? S0 by S0. I can do over here S0 by S0, that will be 1. Then third thing, this term I have to make now dimensionless. So my term is V0 into T. Okay, how I can make it dimensionless? First thing I can simply do V0 by V0. This is gone. Then I have T. Okay, now T is having dimensions of time. So I must have one quantity which can cancel the dimension of time. So dimension of time can be cancelled only if I multiply it with V0. Is this point clear? It will be cancelling only if I multiply it with V0. But when I am multiplying it with V0, then one length unit is also coming into the numerator. So to balance that, I must also divide it with S0. So from here, I can simply say that if I introduce T, then I need to multiply T with V0 by S0 to make it dimensionless. So dimensionless unit of time has become nothing but T star equal to T into V0 by S0. Is this point clear? All are clear with this idea? Okay. Then now next thing left is G. So I must have some combination of S0 and V0 which will be making this G dimensionless. Okay. So G is having dimensions of LT minus 2. So T minus 2. In order to make T minus 2, I am only having this term V0. So I can make it minus 2 if I use V0 square over here. But when I am using V0 square, then I am getting 1 meter square over here and 1 meter is with this. So ultimately I have to use, it is becoming meter cube S0 cube. Is this one clear? How I have found this dimensionless? Say this factor G V0 square by S0 cube is nothing but some quantity alpha. Alpha is some dimensionless group. Is this one clear? If this is the situation, now I can write my equation. This was the dimensional equation. The commensurate dimensionless form, what it will be? S star equal to 1 plus T star plus 1 by 2 G V naught square by S naught cube will become alpha into T star square. How many number of variables I am now left with? S star, T star and earlier I was having 5. Now I am having only 3. So what I can do simply, I can plot S star and T star for first some value of alpha equal to alpha 1, then for some other value of alpha equal to alpha 2, then for some other value of alpha equal to alpha 3, and I will be easily able to understand the trend. Is this point clear? Point is clear what I am trying to say over here. Okay. Now, I was having 3 options to choose. Scaling parameters because I am having S0, V0 and G available. So first I have chosen S0 and V0. Now I can also choose my scaling parameter as S0 and G. I can also choose V0 and G. So my option 2 is S0 and G, and option 3 is V0 and G. So what you do? Try by your own how you can non-dimensionalize all other parameters. What? S, V0 and here what will be other parameters which you have to combine with these in order to make dimensionless. Here the 3 parameters which you have to use are S, T and V0. So this will give you 3 dimensionless variables, and here you have to use S, T and S0. That will give you 3 dimensionless variables. Fine. So till now, whatever the approach I have explained to you, I was able to convey the idea of dimensionless analysis, that why it is important, but I could not explain you the very precise procedure how we can do it. Okay, so what we have done? We have done multiple trials. First I have selected option 1, then option 2, then option 3, and that also there is no systematic procedure for that. Okay, so if you see, the dimensional analysis is having huge amount of literature, and there are many people who have proposed different methods to perform dimensional analysis. Okay, the reason for this is that it is not only applicable to fluid mechanics, but it is applicable to wide variety of situations. Okay, it has applications almost in all the domains of engineering. It has applications in social sciences. It has applications in medical field. It has applications in biological systems. So that's why, depending upon the different areas, people have actually developed their different formats for performing the dimensional analysis. Okay, so one of the popular method which is used in fluid mechanics for dimensional analysis, that is not only fluid mechanics but in all engineering problems, or it can be applied to other areas also, that is called as Buckingham-Pi method. Okay, so Buckingham-Pi method is a systematic method actually which helps us to perform the dimensional analysis. Okay, so in this case we have some steps involved. So first step is we have to determine n. N means number of variables which are actually affecting the physical phenomenon. We have to determine all the n number of variables, and of course we have to list down number of variables affecting physical phenomenon. Please consider this step to be very, very important. If you even miss a single variable, your complete theoretical interpretation of the physical phenomenon will be lost. Okay, you have to include each and every variable which is affecting your system, physical phenomenon. Number 2, determine J. How to determine J? What was J? Number of fundamental dimensions involved. Okay, so what you have to do first, you have to fundamental dimensions involved. So what you have to do first, you have to basically write each and every fundamental dimensions of each and every term, and then you can actually do this. Then number 3, determine scaling or repeating variables. Okay, so how many number of scaling or repeating variables should be there? How many number of less than or equal to J? Okay, so number of repeating variables should be less than or equal to J. Then after that, one important point you have to keep in mind, while you are deciding the repeating variables, your repeating variables themselves should not form a dimensionless group. Have you understood the requirement? So your repeating variables, if you are selecting group of repeating variables, say you have selected rho, v, l and mu. So these are already forming a dimensionless group. So your repeating variables should not form a dimensionless group. This thing you have to keep in mind while you are selecting the dimensionless variables. Another important point, because you have seen from the previous discussion that whatever the repeating variables we are selecting, these are almost participating in all other variables in order to non-dimensionalize them. Okay, so our repeating variables should be some popular terms which exist in majority of the systems. For example, if you have to make comparison in between density and sigma, which one you should choose? Density is very common term. It may appear in a large number of dimensionless groups, but if you use sigma, then it is a very specific term related to free surface flows only. Okay, so if you have chosen your sigma as repeating variable for some scenario, then it may happen that majority of your dimensionless groups will be coming very peculiar, which do not appear or do not take the form of standard dimensionless groups. So that will completely becoming very annoying process to interpret their final fundamental formulation. Okay, so that's why whenever you are selecting the repeating variables, you should focus on the popular terms. And of course, this also comes with the experience. If you keep on doing more number of problems, then you will be able to quickly recall that, okay, what variable you should choose. Similar, so I should choose density. Similar example is if I have, say, velocity of flow one side and speed of sound other side. So which one I should choose? Of course, velocity of the flowing stream, because this is more generic, more popular than the speed of sound. Okay. I must use symbol A because A I think I have used earlier. Okay, then after selecting the repeating variables, we have to now use repeating variables with each remaining variables to form dimensionless groups. So rather than writing in points, it will be better if I can show quickly an example of Buckingham-Pi method. So let me consider that the previous example only. I have F, which is function of density, viscosity, length and velocity. So what is N over here? Please quickly tell me. What is N? 5. 4 are on this side, 1 is on this side. So I have 5. What is J? If you write fundamental dimension for each and every term, you will be finding all MLT are involved. Okay, so J is equal to 3. So my number of repeating variables should be 3 or less than 3. So first we will be trying with 3 variables. So which repeating variable can I choose? Can I choose density? One, I have chosen density. Then second, can I choose length? So these are my repeating variables I have chosen. Now what I will be doing, by using these repeating variables, I have to create the dimensionless groups. So for creating dimensionless groups, I will be writing say my pi1 is one dimensionless group whose dimensions are m0, l0, t0, and this pi1 is nothing but equal to repeating variable rho times a, L times B and velocity times C, and this I have to multiply with, then I have to multiply one additional variable to dimension, make it dimensionless. So let's say my first dimensionless variable is F. Fine. Up to this point, is it clear? Now what I can say that M0, L0, T0 is equal to, what are the dimensions of rho? Times A, L is as it is B, and this V is LT minus 1 power C. And what about F? M. Okay. So now I have MLT on the left hand side, MLT on the right hand side. Let us make powers same. So M, what is power of M? A plus 1. L is minus 3A plus B plus C plus 1. What is T? Minus C minus 2. Okay. So now what I can do? I can equate the powers. So A plus 1 equal to 0. It means A is equal to minus 1. Okay. And what about C equal to minus 2? Then plus 3 plus B minus 2 plus 1 equal to 0. What is B? Minus 2. Okay. So it means that my first dimensionless group is, what is first dimensionless? Rho power A, rho power minus 1. Okay. Rho power minus 1. What is second? V power into F, which is F by rho L square V square. I have talked earlier without doing this analysis. Okay. Then what about second dimensionless group? Rho A LB VC times mu. Please tell me. Rho times A means M L minus 3A, LB, LT minus 1, C into mu. Earlier I have told you, what was the dimension? Please tell me fast. Where is mu? L minus 2 and L will become L minus 1. So M L minus 1, T minus 1. Okay. For mu it is M L minus 1, T minus 1. Please tell me now what I will be getting A. A equal to C equal to minus C minus 1 equal to 0. It means C equal to minus 1. What about B? 0 equal to plus 3 plus B minus 1 equal to 0. So from here B is also equal to minus 1. Okay. So ultimately what I will be getting? Finally the value of C will be pi 2 will be equal to mu by rho VL. So which is becoming your second dimensional S group 1 by Reynolds number. Okay. Okay, so now we will be stopping and then we will see.